Well, good afternoon and welcome everyone to Zoomtime Knowledge. This is our free public education presentation series hosted by the James Madison University Lifelong Learning Institute. If I haven't had a chance to meet you in person, I know it's been some time since when we've been able to gather for our normal programming. My name's Rodney Wolfenbarger. I serve as director of the Lifelong Learning Institute. I'm joined today by Sue G. Sue is our program assistant. She is here to help manage the Zoom platform. So if you have any trouble connecting, feel free to use that chat window, the chat feature. You can put a message in there. Sue and I will be here to help you make sure we work out anything that you might be experiencing with being able to hear or see the presentation. A couple other housekeeping items that I want to mention is your microphones are intentionally muted. They will stay muted until the question and response period to follow the presentation. Again, if you have any questions for our presenter today, feel free to queue them up in the chat window. When we get to the end of the presentation, we've saved time for question and answer. So at that point, we will give you control of your microphones. You'll be able to talk to Dr. Ingham and us as hosts directly when that time comes. With that, let me make a brief introduction to today's featured presenter, and then I'll turn it over to Bill. Dr. Bill Ingham grew up in Western New York. He attended college in Cambridge, Massachusetts, and his graduate work was in astrophysics. He was a faculty member at James Madison University for 34 years, teaching courses in physics, astronomy, the honors program, and the history of science. Bill has also taught several LLI courses since 2011, and he has served as a member of our advisory board. Bill, welcome today. We see the title of your presentation, Johannes Kepler, Planetary Laws and Special Tiles. Thank you for kicking off our Zoomtime Knowledge presentation series here in the new year. I know that this program and LLI programs are familiar to you. So Sue and I will be in the background for support, but if you need anything, feel free to let us know. But with that, I'm going to turn it over to you. You may begin whenever you're ready.
Thanks, Rodney. It's a pleasure to be able to speak with folks today. And I noticed as people were being admitted, the names of many acquaintances and friends, and hello to all of them, and hello to all folks that I haven't yet had the opportunity to meet. But I want to talk with you today about Johannes Kepler, his planetary laws, and some special tiles that he's much less famous for, at least among scientists. So in the history of astronomy, there are two important predecessors to Kepler, and their portraits are shown here. The individual at the left is Nicholas Copernicus. In the year of his death, he published a book whose English translation is On the Revolutions of the Celestial Bodies. And in that, he suggested that rather than the Earth being the center of the planetary system, the center of the universe, if we might say today, he said that the sun was the center of the planetary system. He had this published in the year of his death. There's some speculation that he purposely waited until that time because he knew this would not be necessarily well received. A couple of years after Copernicus' death, Tycho Brahe was born in Denmark. He spent most of his career in Denmark, and he obtained the patronage of the king. And there was on the island of Hveen in the North Sea, a huge, for that time, observatory built. And the woodcut at the right shows him sitting at where there's a giant quadrant. You can see a 1/4 arc of a circle there. And he made planetary observations that are considered probably among the most accurate for giving the positions of planets among the stars prior to the invention of the telescope. We'll have quite a bit more to say about Kepler's life in a few minutes, but the other three of the big five are shown here. Kepler at the left, his contemporary Galileo in the center, and then Isaac Newton at right. So one of the things I maybe should say about all of these people, or at least the first four, Copernicus had very likely studied astrology as part of his studies. He seems not to have had much interest in it. Kepler did some astrology, but was disdainful. Tycho did work in both alchemy and astrology, and his point of view was that the stars influenced but did not determine people. Galileo also did astrology, at least early on in his career, but later on he was disdainful of it. He kind of derided astrology in the book that got him in trouble with the Inquisition. It wasn't his attack on astrology that got him in trouble. And Newton did not, so far as I know, practice astrology, but he did practice alchemy. And out of the 10 million words that we know of that Isaac Newton wrote, 1 million of them are about alchemy. And it turns out that in 1693, he actually had a nervous breakdown, and it's believed that it may have had to do with mercury poisoning, mercury being something that you would use a lot in astrological work. So I might back up just a moment to say that Tycho got into disputes with courtiers at the Danish court, and he eventually left late in his life and relocated to Prague, where he was able to set up an observatory under the patronage of the Holy Roman Emperor. Okay, now this slide's got a lot of text on it, but it's just meant to give you sort of a timeline of important events and works in the history of our understanding of the planetary system. So, as I mentioned, in the year of his death, Copernicus publishes this book whose English translated title is On the Revolutions of the Heavenly Orbs, or the Heavenly Bodies. About 65 years later, Kepler publishes the first of two books that I'll mention in an upcoming slide. The English translation of that book is called The New Astronomy, and it includes his analysis of the orbit of Mars in particular, and it turns out that he was able to conclude that there was really no way to use circular orbits and combinations of circles to explain the observations of Mars, and he had made that conclusion on the basis of getting hold of Tycho Brahe's, pardon me, I tend to mispronounce it, Tycho Brahe's observational records, which Kepler was hired as a calculating assistant or a numbers assistant for Tycho, but Tycho was rather jealous of his records. But when Tycho died in 1601, Kepler succeeded him as imperial mathematician, and he got hold of those observations, and the time between 1601 and 1609 was filled with Kepler using that data and trying to figure out how the planets, what sort of orbits the planets could have that would explain the observations. In 1610, the year after Kepler's publication of his new astronomy, Galileo published this Sidereus Nuncius, or starry messenger, or sidereal messenger. And in it, he provided a lot of data based on, a lot of information based on observations with the newly invented, at least for Europe, telescope. Galileo claimed to have invented the telescope, not really so, but he's the one who turned it toward the heavens and was able to show, for example, that in the dark part of the face of the moon, there were points of light, and he interpreted that as mountains sticking up into the sunlight after sunset or before sunrise, mountaintops sticking up. He saw dark regions within what he realized were craters. And because the ancients had regarded things like the moon as perfectly spherical, this was actually controversial as far as those who were kind of in charge of received wisdom. Coming back to Kepler then, 10 years after the new astronomy, he publishes something called The Harmony of the World, which we'll spend most of our time with today. In there appears for the first time what we call the third law of planetary motion. And we'll have more to say about that. But I should confess, I should point out that Kepler did not call these rules laws of planetary motion. That's what we call them looking back. To come back to Galileo, in 1632, he publishes something called the Dialogue Concerning the Two Chief World Systems. And he manages to offend the person who had become Pope, because he puts this dialogue involves three characters, Simplicio, Sagredo, and Salviati. And Simplicio puts forward some arguments that get questioned by Sagredo and cleared up by Salviati. And Simplicio's arguments include some that the Pope himself had made. So Galileo managed to offend the Pope personally. And it was a strong defense. The two chief world systems he's referring to are the Ptolemaic and the Copernican. And he's defending the Copernican, the heliocentric system, and he gets put on trial for heresy. He is forced to recant, and he spends the rest of his life under house arrest. It's about 50 years later that Newton publishes a mechanical description of the solar system, which engineers and scientists use every day to this day. So let's focus in on Kepler. There's sort of 10 events in his life, including the beginning and the ending. And I've highlighted 4 of them in red. He was born in the Duchy of Württemberg. By 20, I should say he was born in humble circumstances. His mother was the daughter of an innkeeper. His father was a mercenary. And his father left the family. I think Kepler saw him for the last time when he was 5 or 6 years old. At age 20, he managed, with the help of a scholarship from the Duke, from the Duchy, he was able to attend university, and he was intending to study, he was intending to become a minister. He also was extremely good at mathematics. And so he studied a combination of subjects. In his mid-20s, he married someone who was a fairly wealthy family. But the wealth was, as I recall, with Barbara Miller's father. So Kepler actually ends up teaching in locally, but by the 30th birthday, he's looking to try to link up with Tycho, because he knows Tycho has this wonderful set of observations. And he gets recruited there. I think it's about a year before Tycho dies. So they have a little bit of a tempestuous relationship in terms of Kepler being hired as an assistant and wanting to work on what he wanted to work on, and Tycho had not always the same idea about what Kepler was going to work on. But after Tycho's death, he does get hold of the data. And as you've seen, by 1609, he publishes these first two laws, which we'll come back to. Kepler had several children with his first wife, but not all, but several. A couple of his children die in youth, as well as his wife, who dies relatively young. He has the practical problem, as many people did at that time, and some still do, of having lost a spouse, but still having some children in the house. And so he needed, his second marriage was to an extent out of necessity, to get some help with daycare, with childcare. But he actually it's 2 years between the time his first wife dies and he remarries. And he actually goes about thinking about getting remarried as kind of dealing with what you might refer to as the marriage problem. He had sort of went at it in a very analytical and rational way. You notice I put in red the start of the 30 Years' War, because this turns out to loom large in Kepler's life. During the 30 Years' War, the territory that was under control of those who supported Catholicism and those who supported Protestantism, that moved back and forth across Central Europe. And there were times when basically Kepler had to leave a town because of that. He was not only, he thought of himself as a good Lutheran, but there were parts of the Lutheran creed that he would not accept. And he ended up being essentially banished from participating in the Eucharist at Lutheran ceremonies because of his sticking to his guns. So let me take just a moment to point out where we're talking about here. The work that leads to the harmony of the worlds, which we're going to focus on, takes place in Prague. And I realize that's a busy map, but if you can see a green X in the middle of a white blob there, that's where Prague is. And it's in what, it's really part of what you would call sort of the greater Bohemia region. It's on the Vltava River. This is obviously a modern day photograph of Prague. And I mention Prague not because Kepler, he lived there for some years, but he did not actually observe. He did do some observations himself, but it was in other locations. The tower that's shown there, the astronomical tower that's shown in the middle image, doesn't date from that time. It dates from a somewhat later time. I want to credit unknown people on the web for the two photographs at the right. The photograph at the left was taken by a good friend, Steve Wisnett, a few years ago. And the next slide gives you somewhat of an idea of doing astronomical observations from a city several hundred years ago was not for the faint of heart. This is a photograph looking up the astronomical tower. And you can, if you look carefully in the upper left of the image, you can see a ladder. And I believe what's going on there is if you go up that ladder, there's a hole that takes you into a little catwalk there. And then there's another ladder that goes all the way to the very top of that. So this is not something you would do unless you were pretty dedicated or a daredevil. So what I want to do now is focus in on the major publications that Kepler produced. And in 1609, when he was in his late 30s, he really had been working on this program for, more than a decade. In what he published in 1596, he really laid out a plan of attack that began to bear fruit in 1609. I should also mention that there are two other publications here, not in red, that if you looked at the diagrams in them, you would see some fairly familiar looking things. So in the optical part of astronomy and in the book Diopters, you will actually find pictures showing what it is that's going wrong when someone is nearsighted or farsighted in terms of a diagram of the eye and how one might correct for that with lenses. He also devised a telescopic arrangement, which is to this day is referred to as the Keplerian arrangement, and is used in some astronomical telescopes. But the thing I want to focus on today, the two things I want to focus on today are his 1609 publication, Astronomia Nova, A New Astronomy, and in 1619, Harmonice Mundi, Harmonious World, or the Harmony of the World. We have to be careful here. The word world includes, as it was thought of at that time, everything out to the fixed, what were thought of as the fixed stars. So it includes the sun and the entire planetary system. It's not just Earth. Okay, so let's very briefly, and there will not be a test. I promise there will not be a test. Let's very briefly look at these laws of planetary motion. What Kepler was able to do with Tycho's observations, particularly of Mars, was to realize that planets don't orbit the sun in circular paths or even combinations of circular paths. They orbit the sun in a very specific curve, an ellipse. And if we look at the diagram at the left, where it shows F1 and F2, those are what are called the foci, the focuses of the ellipse. And the thing that defines an ellipse is that any point on that ellipse, if I add the straight line distance from F1 to that point, to the straight line distance from F2 to that point, that number is that this total distance is the same for every point on the ellipse. So you may recall having constructed an ellipse at one time using a piece of string, two thumbtacks or two pieces of tape and a pencil, and you just trace this out, keeping the string taut. So that's mathematically what an ellipse is. It's one of what are called the conic sections, because if you take a dunce hat and cut it at an angle, cut through it at an angle, you can, the curve you end up with is an ellipse. Okay, enough about that. How does it apply to the planetary system? The sun is at one focus of an ellipse for each planet. The other focus is empty. The planet moves in such a way that the distance from the sun to that planet plus this distance from the other focus to the planet is a constant. And that's what traces out the ellipse. Why was Mars so important? Mars does not have the most elliptical orbit, but it is somewhat elliptical. And the big reason that Mars was so important was that Mars is Earth's neighbor in the planetary system. And so that meant that if Mars's motion is a little bit out of round, sometimes when Mars is close to the Earth at what's called opposition, it's quite a bit closer than at other times when Mars is close to the Earth at opposition. In other words, you can really sort of tell that Mars's close approaches are not all the same. And just to bring it into the 20th century for a minute, the War of the Worlds radio broadcast was done in, what was it, October? Was it Halloween? But it was done following a period of some months when Mars had made a particularly close approach to the Earth and was bright in the night sky. Okay, second law, also published but not under that name in 1609. This is sometimes referred to as the equal areas law. It's a law that says if you draw a line from the sun to any planet and then sweep that line as the planet moves along, area is covered in the orbit at a constant rate. In other words, if the area in this diagram, A1 and A2 and A3 are all the same, if those areas are all the same, it's because the time taken for the planet to go from A to B is the same as the time taken for the planet to go from C to D is the same as the time for the planet to go from E to F. In other words, that line joining the sun to the planet sweeps out equal areas in equal intervals of time. And we can see in practical terms, in kind of rough and ready terms, it's saying that when the planet is far from the sun, it's moving more slowly in its orbit. And when it's near to the sun, it's moving more quickly in its orbit. Okay, but it's a very specific rule that, that Kepler discovered. Okay, this is the third law, harmonic law. Here we have a graph which is a straight line graph. And it only shows 4 of the 6 planets that were known at Kepler's time. But it's a law that says if I take the period of the planet's orbit in years and square it, and I take the cube, and I take the semi-major axis of the planet's orbit and cube it and plot that, I plot the period squared versus, let's call it orbit size cubed, I get points that fall on a straight line. Now, the first 2 laws say something about each planet by itself. This third law is referred to as the harmonic law because it is a rule that connects all of the planets. In other words, it's a rule that applies to them collectively. It relates how long it takes the planet to go around in its orbit to how big the planet is. And this is why you have Kepler calling that book, The Harmony of the World, because he's discovered this law. Now, I want to take just a minute to say that in my years of teaching, I would typically tell students Kepler's laws describe how the planets move. Newton's laws explain why they move that way. But based on the reading I've been doing, I now realize that this should always come with a disclaimer that that's a distinction that we're making looking back from the 20th or 21st century. Kepler believed that his writings not only described how the planets move, but also explained why. Okay, so whereas Newtonians would say, no, he just explained how. And now, with Newton's help, we understand why. So here's Kepler's Harmony of the World. Here are the books in his Harmony of the World. 4 pages. The first 4 pages are a dedication to King James of England. Why in the world? Why does this fellow writing in Central Europe dedicate this to the King of England? It has to do with the basically standing up against Catholicism as far as Kepler was concerned. Okay, so moving on to the 5 books, and this is the counts that are shown there, and the titles refer to an English translation that appeared a little more than 20 years ago now. So book 1 is what he calls geometrical harmony. Book 2 is what he calls architectonic harmony. Book 3, on the origin of the harmonic proportions and on the nature and differences of those things that are concerned with melody. Book 4 is how the stellar rays affect the Earth and affect events. And this is where you would see some astrological material. And book 5, on the most perfect harmony of the heavenly motions. So the 3 laws that had appeared, well, 2 that had already appeared 10 years earlier, and the 3rd one that first appears in the Harmony of the World are in book 5. And physicists and astronomers give most of their attention to book 5. However, we're going to take a quick look at a sample page from each of the books. There's a glimpse of book 1. So you better have your geometry hat on if you're going to follow book 1. It's very dense. Book 2. This is the one that I'm going to be spending much of the remaining time on. This is are some of the figures that appear in book 2, and we'll come back to them. Here's some more figures from book 2. And if you notice in the left-hand image, there are 4 what are called stellated polyhedrons, stellated solids. And those, so far as anybody knows, were invented or were discovered by Kepler. So Kepler is thinking not only in 2 dimensions, he's thinking in 3 dimensions. The figure at the right shows 5 regular solids. They're called the Platonic solids. And these were known to Plato and to the Greeks, but these figured large in Kepler's thinking about the world. Here's book 3, look into book 3. And here he talks about the intervals that sound good musically and the proportions that exist among them in terms of, depending on how you want to say it, in terms of the frequency or in terms of the length of a string of a given type. I didn't include any figures from book 4. Book 4 is the one on astrology. And I thought that this would be interesting to give you a glimpse into Kepler because he's writing about himself here. And he says, the one and only way in which the arrangement of the stars at my nativity operated was that it both polished up the flames of talent and judgment and urged my mind on to untiring toil, as well as increasing my desire for knowledge. In short, it did not inspire my mind or any of the faculties stated here, but roused it. So I guess he thought of the astrological effect on him as being sort of somebody playing reveille at a military camp, that it roused him. Okay, book 5. This is on astronomical and metaphysical harmony. So again, what we have are the Platonic solids, and the way he uses them is, this is the solar system. Here's Saturn, here's Jupiter, here's Mars, Earth, Venus, and Mercury, and the sun at the very center. And what he's doing is he's nesting these different shapes to help define why the sizes of the orbits of the different planets are what they are. Now, nowadays, an astronomer would say, well, the planetary orbit sizes have to do with, natural laws working as the planetary system formed 4.5 billion years ago. Kepler saw the need and the way to incorporate harmony. Not only that, in book 5, Kepler, and my apologies for you having to sort of look sideways to see these notations, but I wanted the musical staff to be the way it should be. What he's doing is showing musical tones that relate to, I think, the rate of motion of the planets at various points in their orbits. So for example, when Mars is at aphelion, there's this note. When Mars is at perihelion, there's this note, and so on. So he actually, you could think of it as he's composed the music of the spheres. So the primary aim of books 1 and 2 in the Harmony of the World was to provide a geometrical foundation. But book 2 gives a systematic treatment of the problem of constructing, boy, there's a 50-cent word, tessellations. That means tiling. It means covering the plane with figures. So he gave a systematic treatment of the problem of constructing all the tessellations formed by regular polygons, a topic that is still of interest to mathematicians. And I will tell you, this was the genesis of the studies I've been doing, which is the genesis of this talk. So I got into it because I was so fascinated by what Kepler did with tiling the plane. So that's what we're going to go into now. So let's look again at one of these figures from the Harmony of the Worlds. Here are all these figures, and some of them are quite remarkable. And the way I want us to sort of approach this is to start by thinking about all the ways you could carve up the plane by using straight lines and arcs and jagged lines. This is actually a photograph of the crazing of a piece of pottery that's been fired. So every set of lines you might use to cut up the plane into pieces would be a different tiling. There are exactly 3 that are called regular tilings, and these were known long before Kepler. You can cover the plane with regular tiling, with triangles in a regular tiling, with squares, or with hexagons. And the thing to notice here is that every vertex, that is every place where lines come together, where the sides of the polygons meet, every one of those is the same as every other one. And that kind of a tiling is called uniform. And we're going to be focusing on uniform tilings that Kepler discovered all of them. And these three had been known beforehand. They're called regular because they use a single kind of polygon. The one at the left only uses triangles. One in the middle only uses squares. The one at the right only uses hexagons. And here are the drawings from Book 2 of the Harmony of the Worlds showing those. Now, why are there only three? Well, it's not hard to figure out. If we think about polygons that are regular, that have every angle and every shape the same, every side the same. If it's a triangle, I think you probably all remember that all of us were subjected to the tortures of Euclid at one time. And you remember that the sum of the angles of a triangle is 180 degrees. And if it's a regular triangle, all of those angles are the same. So they are 60 degrees. And that means you can put 6 of them together and cover around 360 degrees. With a square, the angle is 90 and 4 of them will take you all the way around. If you have a hexagon, those angles are 120 and 3 of them will take you all the way around. And those are the only possibilities. In fact, if the way you prefer to think about things is visual rather than analytic, here are 2 drawings from the Harmony of the World that Kepler made. And he shows at the left, he's drawing pentagons. And what he shows you there is that 3 aren't enough to get all the way around and 4 are too many. And in the one at the right, he's shown 7-sided figures. And there he shows that even 3 are too many. You cannot fit them. Now, I'm going to set aside some of the polygons that Kepler shows because he shows some polygons that are not regular. And that opens up tiling a whole lot more. So for example, here's a drawing that Kepler includes, which has rhombuses, which have 4 equal sides, but they have 60 and 120 degree angles. I'm not going to worry about tilings that involve such things. I'm also excluding diagrams like this. This one has pentagons, lots of little pentagons you can see. It has pentacles, which are those stars, we would call them stars. It has decagons, 10-sided figures, and it has these several fused pairs of decagons, which Kepler referred to as monsters. And Grunbaum and Shepard are modern authors, and they assert that, yes, you can fill the plane with this pattern. I'm not going to try to demonstrate it, but we're going to not worry so much about those. We're going to focus on some simpler things. Okay, the drawing at the left is included as well, but we're not going to worry about tilings where, you see what's going on the left? You have some of the figures ending in the middle of the side of another figure. In other words, they're not edge to edge. The figure at the right is edge to edge because there aren't any places where a line comes in and just ends in the middle of another side, okay? So you get the idea of what edge to edge is? Now the one at the right, it's edge to edge, but unfortunately you cannot tile the plane with that. So let's look at the ones that we're gonna tile the plane with. Now we're gonna go through this in a fairly rapid fashion because a lot of it is visual. So we'll just look at them for a few seconds each and move on. And I want to introduce this by saying, don't blame Kepler for what's about to come. because this is a modern way of thinking about it. So I want to think about a question that you might think has nothing to do with tiling, but the question is, how many animals can fit together around a water hole? And I don't want to worry about predators and prey. I just want to ask about how well they can fit. And it turns out that there is an artist, an amazing artist, who has done a display, which was shown, I think it was in Brisbane, Australia. And this is called Heritage, and it has a whole variety of different species all drinking from this water hole. So now I want you to go from that to this. So imagine that these are 6 polygons. We're going to fit them around. The water hole is going to shrink to a point, and all of the polygons are trying to get one of their vertices in at that point and exactly fill the space. So there's one way. Here are 3 ways that you can use 5 polygons to fit around a vertex. And notice the code. The way these are written by mathematicians is to say, we're going to start with the smallest number of sides polygon that we can find. In each of these cases, it's a triangle. And then we're going to go around the vertex. And so if I go counterclockwise on the figure starting at the bottom, I get 3, 3, 3, 3, 6. If I start with the triangles in the middle diagram, I can go 3, 3, 3, 4, 4. And that's not the same as 3, 3, 4, 3, 4. You'll see there, those 2 arrangements are not the same. Okay, so that's the mathematician's shorthand for that figure. There are 7 arrangements where you can use 4 polygons. There are 10 arrangements where you can use 3 polygons. I did not create all of these from scratch. These are from the writings of Grunbaum and Shepard. But you'll notice that, for example, if we look up here, this is 3, 7, 42. There's a 42-sided polygon that's so big that you can't fit it. But if you take a triangle, a heptagon, and a 42-sided polygon and put them together right there, they will exactly cover 360 degrees. So that's what these are, okay? So altogether, there are 21 different vertices that you can create using regular polygons. 15 of them include some triangles. 10 of them include some squares. 7 of them include hexagons. 4 of them include a dodecagon. And then 2 of them include a pentagon or an octagon or a decagon. And then there are a bunch of others that only contribute to one of those 21. So there we go. We've got 21 arrangements that fit around a vertex. Can we cover the entire plane with any of those arrangements? In other words, can we cover the plane with shapes so that every vertex in the plane has exactly the same surrounding of polygons? That's called a uniform tiling. And the question is, can any of them work? Well, we know that 3 of them work. Triangles, squares, and hexagons work. But if not, of the other 18, if not all of them, which ones can work and which ones can't? And so here we go. This is going to be a whirlwind tour of trying these. So we're going to find the ones that don't work. So in the spirit of Thomas Edison, we're going to find all the things that don't work. And my apologies for the quality of the photographs. I am not a professional photographer, nor am I a graphic artist. And those 4 squares that you see sitting on that big 42-sided polygon, they're paperweights. They've got nothing to do with the shape. They were to hold that big piece of cardboard flat. And so there's the 3, 7, 42 vertex, created and photographed in my own garage. Why can't you use that to cover the plane? Well, if you look at the left, if you try to put on that triangle, let's go back. If I try to put on this side right here, if I try to put another heptagon, I don't get all the way around. If I try to put a 42-sided figure, I get overlap. I can't make them. I can make this one vertex, but then I go to try to extend that and make another vertex the same way. I can't do it. So I'm going to go pretty quickly through these. Apologies if you get car sick. So 3, 8, 24. That one doesn't work either. 3, 9, 18. That one doesn't work either. And you can see on the left, you leave a gap. On the right, there's overlap right there. 3, 10, 15. Nope, that doesn't work either. 4, 5, 20. Nope, that doesn't work either. 3, 3, 6, 6. Nope, can't make that work either. 3, 4, 4, 6. Nope, can't do it. 5, 5, 10. Nope. 3, 4, 3, 12. Nope, no matter how you try, you can't make these things work. 3, 3, 4, 12. That doesn't work either. Now, Kepler had a way to rule out, those were 10 that don't work. He had a way to rule out 7 of them based on that little figure that you see right up there. It doesn't look like any of the others. What is it he's saying? He's saying that if you have a vertex arrangement that has a polygon with an odd number of sides and then 2 other distinct kinds of polygons, you cannot tile the plane. And his reasoning you can see right here. So here's a pentagon, odd number of sides. And here's 2 other kinds of figures, triangle and square. What happens as you go around the polygon? You can go triangle, square, triangle. If I'm going to have a square, triangle, square, I'm going to end up with 2 triangles together. So he finds out that you can rule out 7 of those 10 unsuccessful candidates just directly from that rule. So let's look at the success stories, because these are prettier. So if you want 6, we already saw that one. That's 6 equilateral triangles. If you want 5, any of those 5 will work. If you want 4 regular polygons, there are 3 of them that will work. If you want to use 3 polygons, there are 4 of them that will work, and the other 6 will not work. So now let's actually look at them. And notice that here are the 5 special tiles. These are the only 5 tiles that show up in any of those 11 successful tilings. The triangle, the square, the hexagon, the octagon, and the dodecagon. And if you'll notice, the octagon really doesn't play that well with others. It only contributes to one of these tilings. And now let's look at those tilings. So here are the ones we've visited before: triangles, squares, and hexagons. Why have I shown this twice? The one at the left uses a single color for each shape. The one at the right is what's called a map coloring. You don't let adjacent sides, you don't let adjacent polygons that share sides, have the same color. So in order to obey that rule, you have to use 2 colors in the case of the triangles. And here are some mosaic tilings you can buy that use triangles. Tiling by squares. Again, we have to have 2 colors if we're going to do a map coloring. And here are 3 products that display tiling, regular tiling by squares. And here's the third and final regular tiling, the one that uses hexagons. And notice that we have to have 3 colors if we're going to do a map coloring. And then here are 2 hexagonal tilings, one on that bathroom floor and one created by honeybees. Okay, 6 or 7 tilings that use 2 different shapes. So let's run through these. Triangles and squares. And notice this one, to do a map coloring, we need 4 colors. And it turns out 4 is the largest number of colors you need to color any map. And map makers knew that hundreds of years ago. It was only proven that 4 colors were both necessary and sufficient about, boy, I'm thinking it was a few decades ago. So it was a problem that mathematicians had to grapple with a long time. But it has been proven that 4 is the largest number you need to color any map. Now, this is a little, this I find interesting, that this next arrangement uses the same proportions of squares and triangles as that one, but it only needs 3 colors. And the reason it only needs 3 colors is that none of the squares have sides together, whereas here the squares have sides together. So there you can get by with 3 colors. This one uses triangles and hexagons, and there's only one figure here because we only need 1 color for the triangles and 1 color for the hexagons, and we have a map coloring. This one uses triangles and dodecagons, and it requires 4 colors, 1 for the triangles and 3 colors for the dodecagons. I have to give my wife some credit for not calling the people to put me in a rubber room while I was doing this and painting these and photographing these. I think she thought maybe I had gone around the bend, but she tolerated it. Okay, here's a tiling that uses squares and octagons. It's the only tiling that uses octagons. Octagons just do not play well with others. So they only play well with squares. And you can see that the map coloring uses 3 colors. Okay, this is perhaps the most puzzling tiling of all. This one uses triangles and hexagons, but instead of a relatively small number of triangles, this uses 8 triangles for every hexagon. And the thing is, it's not the same as that one. In other words, this tiling is a mirror image of this tiling. You cannot rotate this one to sit and coincide with that one. They are 2 different tilings. There they are. When you have things that are handed, mathematicians and physicists refer to these things as chiral. So there's a right-handed version and a left-handed version. And there's an example of 2 chiral molecules, and behind them are shown our easiest example of what chiral means, right-handed and left-handed. And there's chiral spirals, one clockwise and one counterclockwise. Now, I want to prove this to you visually. Here is one of the tilings which is not chiral. It turns out that if we make a mirror image, which I have done, and I hope you can see that I've made a mirror image, because there's the mirror image of that, okay? So this diagram is a mirror image of this diagram. I've done one in red and one in black. And if we put them together, you can actually move the one on the right so that it exactly overlays the one on the left. So that tells us that this tiling is the same as this tiling. In other words, if we reflect it in a mirror, we don't get anything different. Here's the one that I said was chiral. So here's this guy with the lots of triangles and the hexagons, and it's the mirror image of this guy. Now watch what happens when I try to put them together. I can match up some of the figures, but not all of them. You see, there are some places where we have only red and some places where we have only black. We don't have red and black coinciding everywhere. So those really are distinct. Not every person who counts these counts them as separate. So we have to say that they're either 11 or 12. If you count them as separate, there are 12 tilings. And I'll take just a moment with this. These two that are a pair are the only tilings among the 12 for which the tiles that border a given tile are not the same for all tiles of that shape. And not being a good geometrician, I don't know if that's coincidental or there's a mathematical reason for that. I do not know the answer. So I'm just making the observation that there's this fact that these two chiral tilings, they're the only tiling where you have tiles that border a given shape not being the same for all tiles of that shape. And as you can guess, that's triangles, because right here, look, this triangle is bordered only by triangles. But this triangle is bordered by a hexagon and two triangles. So that's what I mean when I say not all tiles of a given shape are surrounded by the same kind of tiles. Here are two uniform tilings that use three shapes: triangles, squares, and hexagons at the left, and then squares, hexagons, and dodecagons. Here are two commercially available tilings that use more than one shape. This one uses regular, it's one of the 12 that we've looked at. This one at the right, it's a tiling. It uses octagons and squares, but why is this not a uniform tiling? It's not a uniform tiling by regular polygons because these octagons are not regular. You see why? This side is a lot longer than this side. So those are bigger, those are other tilings than what we really looked at. Now, for a little almost mystical experience, have a look at some of these tilings. I've shown you 11 or 12, depending on how you count them, tilings of the plane that use a single kind of vertex. There are hundreds and thousands of additional tilings that use two or more different types of vertex. All of them are built from these same 5 magic tiles: triangle, square, hexagon, octagon, and dodecagon. And if you venture to Wikipedia, you can find where I got these. I did not draw them. Okay, before we leave tilings, I have to pay homage to the artists and the artisans. The mosaics of the palace known as Alhambra, the red one in Granada, Spain, use tiles of many different shapes and colors, and they're not all regular polygons. And over the centuries, mosaic artists have created works that represent all kinds of things, from celestial bodies to plants and animals. And when I was in college, I was a big fan of Escher. And so I wanted to include this tiling of the plane at the left, which Escher did in 1939. And if you look carefully, you can see it's sort of a threefold symmetry. In other words, there's a pattern of 3 there, and you can find other patterns of 3. But the shape is anything but a regular polygon. At the right is something that was not discovered until the 1980s, by Roger Penrose, who was one of the recipients of the Nobel Prize this past year for his work with Stephen Hawking. Hawking didn't get the prize because they never award the prize posthumously. This kind of a tiling is not periodic. And you can see, for example, this thing is complete. This one is not complete, right? There's these little guys in here, right? But yet it's, you know, I think it's sort of striking and pretty, and it's called, that kind of tiling is called a Penrose tiling. So I want to finish up with just a few slides that artists and artisans have done. Beautiful mosaics from simple tilings. And this is what a person who's not artistically talented ends up with. This was something I created from the tiles that I had made. And notice which one of the 5 is missing. Which one is missing? The octagon, because it doesn't play well with others. It only plays with the squares. And then you can find software online that allows you to do, I did this over the course of a few minutes with an image editor called GIMP. And there are other image editors that those of you who are artistically inclined will know of. So I want to thank a few people, faculty and staff at JMU. I did some 3D printing. And what happened was the 3D printed tiles were used to create molds from which the plaster tiles were made. So I printed a few tiles and then made molds from them and then used plaster of Paris, basically. So those are some people who helped me. The photographs from Steve Wisnett, I appreciate. And if you really want to see some nice photographs of birds and plants and trees and landscapes, I would recommend Steve's blog spot. It's really very, very nice. No Better Life. And the credits, the figures are from the edition that I mentioned. The line drawings of the polygons come from an article in Mathematics magazine. The book by Grunbaum and Shepard, Tilings and Patterns. I have barely scratched the surface of that book in what we've talked about today. And then Wikipedia has some really stunning articles. And if you look for tessellations and tilings, you can find much more. So with that, I'm going to thank you for your patience. I went longer than I anticipated. I hope there might be some questions, but I'm going to throw it open and thank you for your patience.
Bill, thank you. And before you stop screen sharing, I know you have a number of slides. Early on in the presentation, there was a slide that showed 2 illustrations with F1 and F2.
Yes.
If we can get back there, the first question concerns that illustration.
Okay, let me think about the best way to do that. Is that going to be like that?
Yes. So the question here is, if F1 is the sun, how is F2 located?
Yes, that's a wonderful question. It's not that F2 is there by some material object being located there. The modern day mechanical explanation would be that F2 is determined by, if you take any one location for the planet that's moving, how fast is the planet moving and in what direction is it moving? Those 2 things are going to determine the size and shape of the ellipse. And therefore they're going to determine where F2 would be. So let's think about the thing at the left. If you had a planet that was moving in such a way that it was just like a satellite above the Earth, it was moving in a nice circle around the sun. The planet's moving in a nice circle around the sun. That would correspond to F1 and F2 being in exactly the same place. So if I drew a line from the sun out to the planet and then right back to the sun and said that has to always be the same total, that will generate a circle. And so a person who studies planetary systems would say the size and shape of the ellipse is determined by what they would call in technical terms, initial conditions. Mathematically, the size of the ellipse, the semi-major axis, half the long axis, is determined by the length of the string if we were drawing that ellipse. And how squashed the ellipse is determined by how far apart F1 and F2 are. So if F1 and F2 are relatively far apart, you get a long, narrow ellipse. If F1 and F2 are relatively close together, you get an ellipse that's nearly a circle. And in F1 and F2 coincide with each other, you get a circle. And some of you may know the story, I think it's apocryphal, of a chapel in Italy that was elliptical in shape. And it was noticed that there was a parishioner who was always in one of the pews praying when confession was being held. And then somebody realized that the booth was at one focus of the ellipse, and the place where this guy was in the pew praying was at the other focus of the ellipse. And it turns out that you have, with an elliptical shaped wall, you have what's called a whispering gallery. Some of you may know this from a trip to the Capitol of the United States. So more than answered the question. Sorry for a long answer.
Thanks, Bill. At this point, let me stop your screen sharing.
Okay.
And then we'll be able to see some of our friends. They have microphone access if anyone would like to give you a question or comment.
Okay, so I'm gonna, okay. Oh my goodness. Thank all of you for sharing more than an hour with me. I'm sorry I went a little over, but I'm happy for any questions or brickbats. It's really nice to see many of you. And it's comforting to know that if you throw a tomato, you can't hit me with it.
I see Pat and Marcia are unmuted. If you have a question, please go.
Right. I just wondered, Bill, would you be willing to give us an email address where if we wanted to engage in further discussion on this, we would have a way to communicate with you?
Sure, sure. That's my last name, INGHAM, my initials, WH, at jmu.edu. Will work just
great.
They have not cut off my email access yet.
Great, thank you.
Bill Sanders, do you still have an email address? Bill Sanders? Oh, he may not hear me. I can't hear him because he's muted. So please, whoever else wishes to speak, go ahead.
My question is Ann Harahan. My question was, did Escher study Kepler?
Boy, there's an infinite number of questions I don't know the answer to, and that's one of them. I think it's quite possible. He was, he studied in Europe, and European standards of education, at least for those who were lucky enough to get into the right kind of school, would have been high. And so I'm going to guess that he did, but I don't know whether he studied the geometrical part of Kepler's work, because I think by the 20th century, and as I tried to read in Harmonica Mundi, and I didn't try to read in Latin or German, I tried to read in English, it's a little bit like Beowulf, because it's far enough back in time that the way of expressing oneself was just a little different. So it's a bit challenging. So short answer is, I don't know. Slightly longer answer is, I'm thinking he studied Kepler, but not the geometrical part, not the tilings.
Thank you.
Bill, thoroughly enjoyed it. You're a physicist with an artist's heart. I appreciate that. And I wondered two things. One has to do with alchemy. when you said that they were interested in alchemy, and I know a lot of alchemy had to do with changing things into
right.
Significant metals,
Right.
But what in wasn't a lot of alchemy really just kind of an early form of chemistry? I mean, they were doing all kinds of things with alchemy.
Well, yes, yes. Most all of the sciences have rather, what's the right word I want to use? Scruffy beginnings. I mean, yes. So chemistry was born out of alchemy, and astronomy was a servant of astrology. But I can tell you, having once many years ago at a party, telling a young lady that I had a master's degree in astronomy, and the next thing I heard was a date of the year. And then she kind of just looked at me expectantly, as if I was going to be able to say something about her life. So we tend to be a little defensive about the origins of the modern sciences, but yes, chemistry to a great extent came out of alchemy.
Thanks, I really enjoyed it. Thanks.
Okay, thank you. Good to see you.
Bill, this is Bill Voyage.
Hi, Bill.
Hi, how are you?
Good. Is a chemist going to take issue with what I just said?
No, it's not related to that. You're right,
okay.
by the way, chemistry coming from alchemy. You just mentioned that satellites orbit the Earth in a circle, but we learned earlier on that planets orbit the sun in an ellipse. Why is that?
Okay, I kind of blurred over some things. Satellites orbit the Earth in many of them in orbits that are nearly circular, but there are also plenty of satellites that orbit in elliptical orbits. So a circular orbit is a special case of an elliptical orbit.
Thank you, that works.
Okay.
I'm just looking at whose microphones are unmuted. William Sanders, do you have a question for Bill?
Yes, Bill. The center of your ellipse lies on the line connecting F1 to F2.
Yes.
Now, in that sense, the center of the ellipse is sort of an idealized point that bisects the line connecting F1 to F2.
Right.
When are you physicists and astronomers going to admit that the center of the universe is outside the sun? It's at the center of that. It's an idealized point.
Yes.
Yes. It belongs to the ellipse, not to the sun.
and it's actually also the case that because if we take just for example the biggest planet, Jupiter, the heaviest planet, the most massive planet, what is actually going on is that the sun and Jupiter are orbiting each other, and the sun travels in a much smaller orbit, but the focus of the ellipse that they each orbit, of the two ellipses that are their orbits, is outside the sun's surface. So the sun does actually move back and forth. Think of a healthy adult skater and a child spinning on the ice. The adult's going to move a little bit, but I take your point. The center of that elliptical orbit is not where the sun is. And I would be happy to acknowledge that astronomy seems to be pretty clear that the sun, the Earth is a special but run-of-the-mill planet around a run-of-the-mill star, which is not at the center of even our galaxy. Our galaxy is not at the center of the local group of galaxies. The local group of galaxies is not at the center of what we can see of the universe. But in the large, you can almost take any point on the universe to be equal for learning astronomy.
Bill, another question here is, given an object, we automatically focus some attention on the center of that object.
Right.
Now, where is the center of a tessellation?
I would, for the uniform tilings, I would
it's wherever you want it to be. It's
okay for
any
vertex.
Here is the center.
Yeah.
I would accept your center.
That's right.
Okay.
It's a perfect United Nations General Assembly.
Yeah. Well, thank you, Bill.
Okay.
Bill, I have one more question before we wrap up, and it's in the chat window, but I will read it to you. It says, is there any connection between Kepler, tiles, and the Alhambra?
No, I mean, I felt, especially for those who are artistically inclined, that what I was doing was such a meager subset of all of the beautiful mosaics that could be done, that I wanted to do something. I wanted to include something that sort of acknowledged that there's a whole world of tiling that's beyond what Kepler identified. But I think it's, for me, it was amazing to learn that Kepler had done this, out of his mind, hundreds of years after the Greeks had found those three regular tilings. Kepler found these other 8 or 9, depending on how you count them, uniform tilings, and basically established that there weren't any others. That was them. That was it.
Well, Bill, I want to thank you for your time and thank you for helping us get Zoomtime Knowledge off to such a great start here in the new year. All of our friends who are connected, I've put some information in the chat window, but you'll receive an update by email. We return with our next presentation on February the 16th. That is the Tuesday at noon. And we will be hosting Peggy Emerson, Executive Director of the Harrisonburg-Rockingham Historical Society, who will be talking about their role in saving and sharing local history. Other things to look forward to in February is on Tuesday, February 23rd. Some of you would have heard last year from Dr. Chris Burnson, who is a JMU biology and chemistry professor. We have invited Dr. Burnson back to discuss COVID variants, how the virus is mutating, and address questions and concerns related to new vaccine development. So we hope you'll join us or make plans to join us for both of those presentations. But until then, we hope you remain well and take care. Bill, thanks. Have a great day.
Thanks to all of you. Have a good day.